Hi everyone. So in this video we discuss pooling with a stride, and what stride means is that basically the shift, or what's called the stride, between different pooling units is more than one, right? So you can think basically of two extremes. One is having this stride, right, equal to the pool width, right? So in this example, for example, you have these are detector stages, right? So here, these are the output of the detector stage, the output of the nonlinear activation. And then you pool them. You have a pooling width of 3, right? Because every pooling unit has as input to it three inputs or 3 outputs of the detector stage. And the stride is 2 because the shift between every pooling unit and the next is 2, right? So on one extreme, you could set this stride to be equal to the pool width, right? And that would eliminate any overlap between the different pooling units. So here, for example, this 0.2 unit, right, is common between this the first pool unit and the second pool unit, right? If this, because the stride is strictly less than the pool width. If the stride equal to the pool width, you eliminate all the overlap. That's one extreme. The other extreme is to have basically the stride equal 1, and that's as if you're not using a stride at all, right? So in that case, there will be a lot of overlap between, in fact, there will be an overlap equal to the pool width minus 1. So if the pool width is 10, then there will be an overlap of 9 units between two adjacent pooling units, right? Usually pooling with a stride will strike a balance between these two. What's the advantage and disadvantage of each? So let's discuss the two extremes, right? So of course, like a rule of thumb is that the pool stride should not exceed the pool width. Otherwise, there will be detector units that are useless. So for example, if I have a pool width of 4 instead, if I have a stride of 4 instead of 2, so I remove this 0.2 unit here, then this 0.1 unit here, output of the detector stage, will not have an impact on the further layers in the network, because it will not be connected to any pooling unit. So the extreme that has a lot of overlap have a lot of redundancy among the pooling units, right? So it can lead to a more, let's say, robust representation. A similar effect to what dropout does. So adding redundancy between units. The other extreme, but at the cost of more computation, because more units go in to the next layer, right? So remember, the pooling stage is the last stage of a convolutional layer. So the output of the pooling unit, the pooling stage, or the number of pooling units, this is the number of units that's going to the next layer, right? If I have the maximum overlap, then I have a number of pooling units equal to the number of nonlinear activations. So I have a large number of units going to the next layer. If I have a stride of 2, I reduce that number of units by 2, go into the next layer, and hence an architecture with much less parameters, right? Imagine if the next layer is a fully connected layer, for example, after the convolutional layer. So that will reduce the number of parameters in the next layer by a lot. If I have a stride of 3, then I reduce it by 1/3 and so on. But the advantage is basically you have more overlap, so you have more units connected to the same pooling unit. Now, why could that be an advantage? It could enhance learning, right? Imagine, for example, I'm using max pooling, right? So this unit here, consider the first pooling unit. It doesn't matter where the first detector stage output is 0.1 or 0.2, because the output of max pooling will always be 2, right? So in effect, this maximum unit is blocking the learning of the other units, and hence all the parameters connected to the other units, right? So all the parameters going off here and all the parameters going off here, right? But in that example, all the parameters going to the unit with 0.2 still have a chance to learn, because this unit is affecting another pooling unit, and where it's the maximum, right? So when you maximize the overlap, when you have a smaller stride, you maximize the overlap between the pooling units, that will enhance or increase the likelihood that all the input units, the detector stage units, right, the output of the convolutional kernels, all these units are actively learning, right? But when you decrease the overlap, you have a computational advantage, and at the same time you increase the likelihood that some units, right, will be blocked from learning. Why is that a problem, blocking units from learning? Because it makes your model more sensitive to initialization. Because initialization is what will determine which units in the first few iterations will be actively learning, which ones will have the maximum, right? If you are using max pooling. Even if you are not using max pooling, the same gist or the same insight can hold, but not in as explicitly as when you are using max pooling. Increasing redundancy gives you a more robust representation. Decreasing redundancy between the units will give you more diverse representation. That could even have advantages even beyond the computational advantage. A diverse representation between the pooling units can improve generalization, right? And that goes hand in hand with a pattern that you will see always, and you have seen already throughout this course, which is sometimes when your goal is improving the computational efficiency, it comes with the package that you actually improve generalization, because you tend to sparsify the learning process, and that creates a more diverse representation versus a more robust, right, with redundancy. And the more diverse representation will typically improve generalization, because you are less sensitive to very small changes in the training examples. Now, a few more comments before we finalize is basically this stride. Pooling with a stride could be essential for handling varying input size, and that's in general, as you will see later also in this section, that's one of the advantages of convolutional layers, is that a convolutional neural network can adapt to varying input size, and we'll see later when that is appropriate and when it is not. But pooling with a stride can be a mechanism to enable that by varying the stride width with the varying input size, to accommodate the varying input size, so that the further layers have the same dimensions regardless of the input size. And we'll also in the video after next, we will take an example where we basically discuss in more detail the details of that. The last thing is that this is a really an active open area of research on all the variants of pooling and pooling with a stride that could be implemented, including to make these things dynamic, the pool width as well as the stride, as well actually as the connectivity itself of the pooling unit. So here it was, this is fixed pooling connectivity, but the graph going from the detector stage units to the pooling units could itself be a dynamic graph that changes during training from one iteration to the next. Thank you.